z having order m, which is given by 1 by m minus 1 factorial limit z approaches a d power m minus 1 divided by dz power m minus 1 into z minus a whole power m into f of z. So this is the formula we are going to use to find the residue of the given function f of z. And in the problem given, your f of z is 1 by z minus 4 into z plus 1 whole power 3. So my first step is I want to find what are the poles of the function f of z. So to find poles of the function f of z, a simple way is you take the denominator of the function f of z and equate to 0 and solve for z. So here the denominator of f of z is z minus 4 into z plus 1 the whole cube equals 0. So when I solve these two factors, I am getting two poles. When I solve the first factor, I am getting z equals 4, which is a pole of order 1, or I can say it is a simple pole of f of z. Coming to the second factor, when I solve z plus 1 the whole power 3 equals 0, I am getting z value equals minus 1 3 times. So I can say z equals minus 1 is a pole of order 3. That is, it is repeated 3 times. The particular pole z equals minus 1 is present 3 times in the function f of z. So it is having order m equals 3. Now we are going to find residue for each poles separately. Let us see what is the residue for the first pole. That is a simple pole of f of z. Z equals 4. You take the formula given, the formula which I boxed above. In the above formula, we are going to substitute z equals 4. That is, a value is replaced by 4 in the given formula. And the corresponding order for the pole z equals 4 is 1. It is a simple pole. So therefore, residue of f of z at z equals 4 equals 1 by 1 minus 1 factorial limit z approaches a value is 4 d power 0, because m value is 1, so m minus 1 becomes 0, d power 0 by dz power 0, z minus 4 power 1 into f of z. F of z is 1 divided by z minus 4 into z plus 1 power 3. Now we can simplify the factor. Z minus 4 and z minus 4 gets cancels, and we know that 0 factorial is 1 and d power 0 by dz power 0 is nothing but 1. So we left out with limit z approaches 4 1 by z plus 1 whole power 3. So we are going to apply limit for 1 by z plus 1 whole power 3 when z is approaching 4. So therefore you just replace z value by 4 in the given function. So the answer is 1 divided by 4 plus 1 whole power 3, which is 1 by 5 cube, which is 1 by 125. So I am able to find residue for the first pole, which is 1 by 125. Coming to the second pole of f of z, the second pole of f of z is z equals minus 1 and the corresponding order is 3. So therefore I am going to substitute a value as minus 1 and m value as 3 in the formula for residue. So therefore res of f of z at z equals minus 1 equals 1 by m minus 1. M is 3, so 3 minus 1 factorial. Limit z approaches a. A here is minus 1, so z approaches minus 1. D power m minus 1. So m is 3, m minus 1 is 2. So it is d square by dz square into z minus a power m. So z minus of a is minus 1. So z plus 1 power m. M is 3. So z plus 1 whole power 3 into f of z. F of z is 1 divided by z minus 4 into z plus 1 whole power 3. Now we can cancel z plus 1 whole cube with z plus 1 whole cube. After cancellation, we have 1 by 2 factorial. 3 minus 1 is 2, 2 factorial. Limit z approaches minus 1. So we can convert the second order derivative with respect to z into product of two first order derivative, which is d by dz into d by dz of 1 by z minus 4 again. So if I differentiate a function with respect to z, you make sure that the variable is present in the numerator, but unfortunately our function has z in the denominator, so you bring it to the numerator. So when I bring z minus 4 in the denominator to the numerator, I will get z minus 4 power minus 1. So again 2 factorial is 2, so I have 1 by 2 limit z approaches minus 1 d by dz, differentiation of z minus 4 whole power minus 1. So apply the power formula for derivative. So the power comes to the base minus 1 into z minus 4 power minus 1 again minus 1, so it is power minus 2. Now before doing the next differentiation, we remove the constant term outside the derivative as well as outside the limit. So here minus 1 is the constant term, so I can pull it outside the limit. So I have minus 1 by 2 outside the limit, minus 1 by 2 limit z approaches minus 1. Again differentiate z minus 4 power minus 2 with respect to z. Again use the power formula. So when I differentiate, the power come to the base. So minus 2 into z minus 4, the power is decreased by 1, minus 2 minus 1, which is minus 3. So I have z minus 4 power minus 3. Now you can see we have minus 1 by 2 outside, and after differentiation we have minus 2 in the numerator. So both the terms get cancels. So we left out with the limit z approaches minus 1, z minus 4 power minus 3. So now we can replace z value by minus 1. So we will get minus 1 minus 4 power minus 3, that is minus 5 power minus 3. So if the power is negative, you are going to take reciprocal for the base. Here the base is minus 5. So the reciprocal of minus 5 is 1 by minus 5. So 1 by minus 5 to the power plus 3. So minus 5 cube is minus 125. So therefore the residue for the second pole z equals minus 1 is minus 1 by 125. So the correct option is option B, 1 by 125 and minus 1 by 125. So these are the residues for the poles of the function f of z. Coming to the fourth problem. Again, fourth problem is also a problem based on residue concept. For f of z equals sin z by z square, the residue of the pole at z equals 0 is, and this is a problem which is coming under 2 marks question. So they are given a function f of z and they are asking you to find what is the residue for the pole z equal to 0. So first of all, let me check what is the order of the pole z equal to 0 in the function f of z. So to find the order of the pole z equal to 0, you take the denominator and of f of z and equate to 0. So you'll get z square equals 0. So z value is 0, 0. So 0 is repeated 2 times. So I can say z equal to 0 is a pole of f of z of order m equals 2. So now we can appeal the residue formula. I am just writing the residue formula. RES f of z comma z equals a, and a is a pole of order m, which is given by 1 by m minus 1 factorial limit z approaches a d power m minus 1 by d z power m minus 1 into z minus a power m into f of z. So here f of z is sin z by z square, and z equals a equals 0 and m equals 2. So m minus 1 is 1. So therefore we can substitute all these values in the above formula. So therefore residue of f of z at z equal to 0 is given by 1 by 1 factorial limit z approaches 0 d by dz of z minus 0 power 2 into f of z, which is 1 sin z by z square. Now z square and z square gets cancels. So we left out with 1 by 1 factorial, which is 1 limit z approaches 0 d by dz of sin z. That is differentiation of sin z, which is cos z. So therefore I have limit z approaches 0 cos z. So now we can apply limit by substituting z value as 0 in the function cos. So I will get cos 0 and cos 0 is 1. So therefore the residue of the function f of z sin z by z square at the pole z equal to 0 is 1. So which completes the fourth problem. Coming to the fifth problem, if C is a circle of radius r with the center z0 in the complex plane, and if n is a non-zero integer, then the closed integral over C dz by z minus z0 whole power n plus 1 equals option A 2 pi nj, option B 0, option C nj by 2 pi, option D 2 pi n. Again, this problem is a problem from multiple choice question, carries 1 mark. So before solving this problem, let me explain the concept which is needed for this particular problem. So first of all, I am going to state the Cauchy's theorem. If f of z is an analytic function and f dash of z is continuous at each point within and on a closed curve capital C, then integration over capital C f of z dz equals 0. The Cauchy's theorem says, if you take function f of z which is analytic inside and on the closed curve C, and its derivative f dash of z is continuous, then I can say integration of f of z dz is 0. Coming to the second theorem, Cauchy's integral formula. If f of z is analytic within and on a closed curve capital C, and if A is any point within C, then f of A is given by 1 by 2 pi I integral over C f of z dz by z minus A. Or I can rewrite the formula as integration over C f of z dz by z minus A equals 2 pi I into f of A. So generally when we solve problem, we are going to use the second form of Cauchy's integral formula, because usually to apply Cauchy's integral formula or Cauchy's integral formula for derivative, the question contains only integration. So therefore I am rewriting Cauchy's integral formula like that. And coming to the next one, Cauchy's integral formula for derivative. Integral over C f of z dz by z minus A whole power n plus 1 equals 2 pi I by n factorial f n at the point A. So where f n represents nth derivative of the function f at the point z equals A. And now I am going to tell under which situation we are going to apply Cauchy's theorem, under which situation we are going to apply Cauchy's integral formula and Cauchy's integral formula for derivative. So if the function present inside the integration is analytic everywhere, then we can use the Cauchy's theorem and we can say the integration for the given function is 0. Coming to the Cauchy's integral formula, if f of z is having a singular point z equal to A which is present inside C, and the important thing is the singular point or pole z equal to A must be having order 1, then we can apply the Cauchy's integral formula. So if the pole